Hey, welcome back to assembly language. This is computer organization COSC 2325, chapter 2. We'll be talking about the 86 processor architecture. In this particular video, we're going to go over the general concepts, section 2.1 in your book, which covers the basic microcomputer design, instruction execution cycle, reading from memory, and how programs run. So some of the things that we'll look at within these bullet points is we're going to discuss some of the basic operations that take place inside the processor when the instructions are executed. We'll talk about how programs are loaded and executed by the operating system. We'll look at a sample motherboard layout and give some insights into the hardware environment of the 86 system, and then how layered input-output works between application programs and operating system. So here is just a picture of a motherboard. This here is the CPU socket. So this is where your CPU would be locked in. So this is just to give you an overview of some of the parts of the computer, which there is a section in your, there's a section in your book towards the end of the book that goes over some of the components of the system. But the main point of this video is just to talk about how instructions, and when you open up a program, how those instructions move from, let's say, the CPU and RAM. So we'll talk a lot about the CPU in this particular video. So this is a closer look at a CPU. And if you see in this picture, there's some pins here in your CPU, and this is where the data travels to the hardware. So here we have the basic microcomputer design. So just a picture of the design of your CPU is right here. Here we have RAM, input, output, and this is just like, this could be keyboard, this could be printer. Let me you can see my mouse as I move it, I'm pretty sure. Okay, so the basic microcomputer design contains, again, your central processing unit, memory storage unit, which would be RAM, input-output devices, but it also contains some buses that we're going to look at in detail. These are, like, this is the data bus, control bus, and the address bus. This is called the system bus. Now the CPU itself has 3 parts. It has a clock that synchronizes the CPU operations with other system components. So it has a clock that's going to synchronize those instructions that get sent to RAM, or maybe an address that gets sent to RAM or data, and also to input-output devices. And then we have the control unit, which coordinates sequences of execution steps in executing machine instructions. So the control unit would coordinate which, if we have a program and we have certain instructions that we need to follow in a certain sequence, it coordinates those, that part. And the ALU performs arithmetic and bitwise processing. So arithmetic would be just, addition, subtraction, but also logical operations. And then bitwise processing would be looking at the bits, the ones and the zeros, and it could be like shifting the bits. So it's just processing ones and zeros. Here in this picture, you also see that the CPU has registers, and the registers are just a limited number of memory locations that sit on your CPU. Depending on the size of CPU, whether it's like it's 32-bit or 64-bit, etc., depends on how many registers we have available and how big those registers are, like how much information can we put in one register. But it is limited storage, like it says on here, because there's only a certain number of registers. And then, again, the CPU does all the processing of the data. And we'll look at that in more detail in just a second. So in this picture, on the left-hand side, you have your CPU. Here's the arithmetic logic unit, control unit, and your registers. And here we have main memory. So memory is always very close to the CPU because whenever you open a program on your computer, the instructions, there's a certain amount of memory that's allocated to the instructions of that program. And then the CPU is the one that's going to process the instructions. So we've got to go to the CPU, we got to go back to memory, and go back to the CPU, back and forth. Now, we'll also talk about cache memory, but for right now, let's just look at main memory. This here's main memory, directly accessible by the CPU, and it's accessible by the CPU through a bus system. A bus is a collection of wires through which data is transmitted. So these three lines that you see here would be one bus system. Okay, so one bus would be these three lines together. So the speed of a bus is measured in megahertz. The size of a bus is its width. So this right here, from these three lines, are the width of this one bus. If we have, and the width is how many bits it can transfer at a time. So since there's only three lines here, this means we can only transfer 3 bits at a time. So if we have a 64-bit bus or a 64-bit computer, it means that when we transfer data, we can transfer 64 bits at a time. We're going to be programming for 32-bit systems. So that means we'll be able to send 32 bits at a time. So of course, the more bits that we can send at a time, the faster it is that we can process information, and also the bigger value that we can send through a bus. If we had to send a value to memory or get a value from memory back to the CPU. So again, I use the word lines. That is the correct term to use for each one of these wires. It's a line. Again, the width is the size of the bus. The 32-bit system has 32-bit width buses, and it means it can transfer 32 bits at a time. So again, here would be the CPU. We're looking at RAM here again. Each of these arrows is we're looking at a different type of bus. So there's the system bus. That terminology is used like an overarching term for the different types of buses that the computer contains. So the system bus includes the address bus, the data bus, and the control bus. So here the red, well, the other thing about buses is that they can be unidirectional or bidirectional. So meaning that the bits or the ones and the zeros can go one direction from CPU to RAM. So they can be one direction only, or they can go both ways from RAM to CPU and CPU to RAM. So the address bus is this red arrow, and the address bus sends a memory address along the bus from the CPU to memory. So this is unidirectional. CPU will always send the address through the address bus. And it's going to either fetch or write data. So it's either going to get data from RAM and bring it back to the CPU, or it's going to write data to RAM. The CPU needs to tell RAM the address where to write to, or the address where to read from. Now, this control bus back here, the purple, if I send an address to RAM and I want to write to the address, then through the control bus, there's going to be a status message that gets sent. There's going to be a flag that gets set to say, hey, I am reading from RAM, or I'm writing to RAM, whatever address I pass it. So right here down here in this little picture where you see clock, read, write, interrupt, the control bus can, if I send an address to RAM and I want to read from that address, then we would set this read here to on, which would be 1. If I want to interrupt, so it carries a command from the CPU, status message to other hardware devices. So if I want to interrupt, let's say a printer, then this flag would be set. So the control bus, so if we have a look at 32-bit system or 64-bit system, the control bus does not have to be 32 or 64 bits because it 62 or 32 wires. It doesn't need that many wires because we don't have that many status messages. But the address and the data bus do have to be the size of like 32 or 64 bit, depending on the system that we have. It has to be that many lines. So the data bus sends the actual data to and from memory, so it's bidirectional. So let's say that I want to write a value to RAM. The CPU will send the address. It will send the data that it wants to write to that address. And here through the purple arrow through the control bus, it will send this status message of 1 for writing. So one of the things that we said that part of the CPU has the control unit, the CU, the ALU, the arithmetic logic unit, the registers, and a clock. The clock is very important. The clock synchronizes all the CPU and the bus operations. It keeps everything at a certain pace and called a frequency. So in this picture here, we see this cycle. The cycle actually begins here, and one cycle would end here. So that's one cycle down, here's another cycle. A machine clock cycle measures the time of a single operation. An operation can take one clock cycle, two clock cycles, three, four, depends. The more clock cycle it takes, the slower that operation is processing. But each instruction has to take at least one clock cycle. One clock cycle has to happen, even if it's, faster than a clock cycle. Everything takes at least one clock cycle. Clock helps in determining the speed of the CPU. We'll look at that in a second here. I think that's the last slide of that. Okay, so a few more things about the clock. So there's two types of clocks. So we have the system clock, and we have what's called the RTC, or the real-time clock. So the system clock is what your operating system manages. So when you turn on your computer, your operating system has the correct time. And that time is coming from the real-time clock. And the real-time clock is actually a chip that sits on your motherboard that is battery powered. And so even if you turn off your computer, that system clock is still, the real-time clock is still working. So the system clock is the one that then uses the real-time clock to get the current date and time. So the system clock refers to the timekeeping mechanism within a computer system, again, that is managed by the operating system. And it updates only while the system is powered on, of course. And the RTC is dedicated hardware, is a chip. So when we turn off our system, there's a battery backup to maintain accuracy. And then again, the system clock relies on the real-time clock to set the initial time the system boots. As far as the clock cycle, one clock cycle is equal to one. So one clock cycle is 1 hertz, and 1 hertz it's 1 hertz in 1 second. So if we say that the clock cycle is 1 megahertz, it would be 1,000 hertz. And then if we say 1 gigahertz, it would be 1 billion hertz. So if we have an instruction that executes, let's say, 1 megahertz, then it takes 1,000, because it's mega, so it takes 1,000 hertz to execute that instruction. So the next thing we're going to look at is the instruction execution cycle. And so a single machine instruction doesn't, so let's say that I open up a program, and we've got the first instruction of our program. So how does that instruction actually get executed? What are the steps is what we're going to look at. So the first thing that we want to note is that when you open a program, like I said earlier, the instructions of your program go to memory. So there's a certain chunk of memory that's allocated to that particular program. There's also a stack that contains the instructions in the order that they need to be executed. And if you if you want to imagine what the stack looks like, let me pull up a pencil here. Think of a stack like an array. And each element of the array, so this is an array. So this would contain an instruction, and this will contain an instruction, this will contain an instruction. And it's actually a stack, so that means that your first instruction, so if your first instruction is here, your second instruction would be here, and your third instruction would be here. And so since it's a stack, equals that, we get we have something called an instruction pointer. And actually, I'm going to put this incorrect. We do have an instruction pointer, but here we have a base pointer. So the stack has a base pointer. It's here. This is the instruction. The instruction gets moved to the instruction pointer. And really, it's not the instruction that's here, but it's the address of where that instruction is. So we have a stack with an address of the instruction. So that address, let's say it's address 1. When I'm ready to execute this instruction, it gets moved to an instruction pointer. This instruction pointer here it's one of the registers. So it sits on the CPU. So on the CPU, you have the address to where the next instruction is going to execute. The instruction pointer always contains, as something is running, it contains the next address of what needs to run. So it's like ready. This minute this one's done, it has that one ready to be fetched. So the instruction execution cycle, the first step is to fetch the instruction from the instruction queue. So this is my instruction queue right here. Then we decode that instruction by looking at the binary patterns, and it fetches operands if it has any operands. So let's say that the instruction, this first instruction is A equals hourly pay times number of hours. I'll put HP times H. Not very good variables, but it's okay. So here in this equation, or expression, I have 1, 2, 3 operands. So we fetch the instruction from the instruction queue. We decode by looking at binary patterns. We fetch the operands if we have any. So we have 2 input operands and 1 output. This is an output operand. These are input operands. And so we fetch these 2 input operands. So it's got to go. So basically at the decode, think of the CPU. It's got to put the address of where HP is in memory. And then it's got to bring back the data in HP. And also H brings back the data from HP and H to the arithmetic logic unit, so it can then multiply those 2 values together. And then at this point, it executes the instruction. And so it takes the 2 input values and it stores the result does the calculations and stores the result into pay. And that in this particular step, the address of wherever pay gets passed along the address bus with the amount of pay, and they go to into the RAM, and that value stored into the variable pay. Also, something that we're going to be looking at are things called status flags, and status flags are also part of a register. There's an e-flags register that contains status flags. So let's say that when you multiply this, the value came out to 0. There's a status flag that gets set that says that your calculations yielded a 0. Maybe it came out to a negative number. Then there's a status flag that gets set that that this calculation is a negative value. So there's status flags, and those status flags are really useful. They're used for like whenever you do conditional statements or loops, we can check for things like, was the equation come out to 0 or a negative number. And there's a lot of different status flags. So the instruction execution cycle, again, has 3 steps. And in your book, you'll look at the information on the 3 steps. Let me... I don't have it here on the slides, but in your book, it has all the different steps. So make sure that you review that and try to kind of understand the 3 steps. We'll be talking again about the instruction execution cycle throughout the whole entire semester. For now, you just need to know these steps. Okay, reading from memory. Multiple machine cycles are required when reading from memory because it responds much more slowly than the CPU. So if I want to read from, if the CPU has to read from a register, where the registers sit on the CPU, it only takes one machine cycle or 1 clock cycle. But if I have to go to RAM to actually get, whatever I need, which most likely that's going to happen, then it's going to take more than 1 machine cycle. It take 2, 4 machine cycles. But remember, like if you have a machine that's like a 1 gigahertz, then it is 1 billion instructions per second can be actually processed. So step 1, we place the address of the value you want to read on the address bus. And we went through these steps. We assert or we change the value of the processor's read pin. So remember, this is the control bus. The control bus has those different flags, and 1 means it on, 0 means off. So because we are reading, we want to set the read pin on so that we know that we're not writing to this address, we're reading from it. Then we wait 1 clock cycle. We always have to wait 1 clock cycle to get something from, or more, from memory. And then we copy the data from the data bus into the destination operand. So again, this is reading when reading from memory. So for example, when we said pay equals hourly pay times hourly pay times number of hours, then if I want to go get the number of hours from memory, I would pass the address of where that variable is in memory, and it would return back how many hours. So, and then multiply it and then assign it to whatever it needs to be assigned to. All right, so earlier, I said that whenever you open a program, the instructions of that program are put into memory. So there's a certain amount of memory that's allocated for those instructions and also for anything that we want to do for that program. So when you have multiple processes running, multiple programs running, the programs have their chunk of memory so that you can, if you have to create a variable, as your program is running, you can allocate memory, deallocate memory, and that chunk of memory doesn't collide with this other process because it's in a different space in memory. So, so one of the things to make things go a bit faster, not have to always go to RAM, is that part of this instructions can also be put into cache memory. So cache memory is a high-speed, expensive static RAM. So cache memory is static RAM, and your main memory is dynamic RAM. Dynamic RAM just means that you have to refresh the memory. Static means you don't. And cache memory is just a smaller amount of memory. And the reason it's smaller is because it sits on your CPU and it's more expensive. We have cache memory that sits on the CPU, and we also have cache memory that sits outside of the CPU, very, very close to the CPU, and uses a very high-speed bus system to transfer the data. So between the cache sitting on the CPU and right outside of the CPU, they kind of work together to make things go by faster when we're processing instructions. So that's what we call level 1 cache versus level 2 cache. There's a small video that a link that I placed within this presentation. If you want to watch that video. It talks a little bit about cache memory, but other things that are in cache memory would be like if you use something often, it goes first to cache memory to see if that information is there, that it needs that data. And if the data is there, then it's able to get it quicker, and that's called a cache hit. If that data is not there, it's called a cache miss, and then it goes to RAM to find the data. Okay, and then this slide shows how a program runs. In your book, you also have all the different steps. It explains these steps, and I definitely want you to look at that and make sure that you understand. So here we have the user. The user sends a program name to the operating system. So I want to open Microsoft Word. So I send that name gets sent to the operating system that I want to open Microsoft Word. The operating system will search for the program in the current directory or some particular path to find the program. Let me just look on here to make sure I don't miss any of the steps that I was going to tell you about this, because there's quite a few of them. Okay, so when the program file is found, the operating system will retrieve basic information about the program file from the disk directory, including the file size and its physical location on the disk drive. Then the operating system is going to determine the next available location in memory that loads the program file into memory. This is where we allocate that amount of that block of memory for the program. And then there's a table called a descriptor table where the program size and the location is logged. So the size and the location of the programs are logged into a descriptor table. Additionally, the operating system may adjust the values of the pointers. You don't have to know that. Then the operating system begins executing the program, the very first instruction of your program, which is the entry point of your program. As soon as the program begins to run, then now we call that a process. And that process, the operating system assigns a process ID. So if you want to look at the process ID of your programs, you can search for Task Manager, which I just did a few minutes ago. So it's going to be here, but you'll just type Task Manager. It comes up. And then you're able to see, if you click on process of the task manager, you're able to see all the processes that are running and how much memory and CPU it's taking. You can also see the process ID, the details. So here's a process ID for the unique process ID that's assigned to each one of them. So here's our directory, and that's where we enter that's where the operating system will enter the processes that are running. Then the process runs by itself. It is the operating system's job to track the execution of the process. And then let's say that I'm running this Microsoft Word program and I decide that I want to print something, then it's the job of the operating system to do that job. So it's tracking the resources that this Microsoft Word program needs, like printing or writing to something. Then when the process ends, it is removed from memory. So that block of memory is deallocated and available for another program. Okay, in the next video, we're going to look at the 32-bit processor architecture and the 32 and how the 32-bit processor manages memory. And then here, these are all the topics for the chapter. We'll look, even though we're not going to be programming for the 64-bit processor, we'll just look and see what the differences are between the 32 and the 64-bit. And we'll look at the components of a 32 of the Intel architecture 32-bit microcomputer. So this would be the components of that sit on the motherboard. And lastly, the input-output system. Okay, see you in the next video. Thank you.